Hello everyone, this is Chang from Western New England University, and I'm really glad to have a presentation about engineered cementitious materials for durable railroad cross ties. Today's presentation is to show you how we were developing the new ECM for durable railroad cross ties. Also, these outcomes can be generally used for any kind of the new concrete materials development. Anyways, the outcomes are based on the two different projects. One is project number 3.5, prevention of stress-induced failures of pre-stressed concrete cross ties of the railroad track structure. The other project is the transportation infrastructure monitoring and assessment for the enhanced life. When we worked on these projects, we needed to decide the two objectives. One is to commercialize the developing ECM to support the industry. Also, we knew that we needed to test several aggregates available in Massachusetts, and this was a pretty good chance for us to check whether we can make the high-performance ECM by using local materials. Also, the second objective of this research is to develop a method to evaluate structural performance damaged by reinforcement corrosion. Therefore, the outcome of the second objective is to use for regarding durability aspect for the developing ECM. We initiated this project. We explored several structural requirements provided by the related area. American Railway Engineering and Maintenance of Way Association, which is ARIMA, provided several guidelines. First of all, the strength should be greater than 7,000 psi at 28 days, and minimum service life of the cross ties should be 10 years. Also, there were several quality control requirements related to the concrete and steam curing temperatures. In addition, ARIMA requires several durability requirements about the alkali aggregate reactivity, delayed Ettringite formation, freeze and thaw damage, and corrosion. However, it's really hard to follow those rules because they provided the related ASTM standards. However, ASTM does not require any specific structural performance related to the durability damage. ARIMA also refers to the American Concrete Institute 318 code for designing the mixture proportions. However, if you take a look at those tables, ACI just provides different exposure conditions for freezing and thawing, sulfate condition, which is related to the delayed Ettringite formation, and the contact with the water conditions, which is related to any general chemical attacks, and corrosion protection of the reinforcements. Also, if you take a look at the table on the right-hand side, according to the different exposure conditions, they just provided us the maximum water cement ratio and the minimum the strength condition. Therefore, any mixtures satisfying both maximum water cement ratio and minimum strength conditions, and they will satisfy particular durability conditions. However, interesting point is that if you take a look at on the very bottom, maximum water cement ratio of the 0.4 and the minimum strength requirement for 5,000 psi, if you satisfy those two conditions, and that particular mixture will satisfy any kind of the durability conditions as well. Massachusetts Department of the Transportation provided the qualified construction materials list, although they are not specifically about the railroad cross ties. However, the mixture proportions can be used for any kind of the construction purposes. Anyways, if you take a look at the list, 852 concrete mixture designs manufactured by 66 concrete producers were already approved. If you take a look at the distribution of the strengths of those mixtures, 6 out of the 852 satisfy both ARIMA and ACI 318. In other words, those mixtures can be used for the concrete cross ties. Then our research team thought about, do we really need to develop the new ECM? And that was quite interesting research question for us. However, the durability issues of concrete cross ties have been reported in news historically. 1989, New York Times reported the crumbling of the concrete cross ties in Metro North Line. Also, in 2007, MBTA filed a $90 million lawsuit for defective concrete ties. MBTA wanted to have the 50 years of a life cycle for the concrete cross ties. However, right after 10 years of the operation time, all the cross ties had a significant issue related to durability. Therefore, that issue impacted on the operation of all trains. So then the research team realized that we still need to develop the ECM for durable railroad cross ties. However, we needed to find out where to start. When summarizing the mixture design parameters, conventionally we use the durability conditions provided by the ACI 318 code. Again, that was just different exposure conditions rather than the durability requirements. Also, the strength, which is a structural requirement, and slump for workability was the design parameters, and air content related to the workability and the freeze and thawing performance was one of the design parameter. And maximum aggregate size was a design parameter. However, that number is somehow based on the aggregate size distribution. However, when we developed the new ECM, we thought about the new design parameters. Strength, as a conventional, is one of the parameters that we have to consider. And instead of the slump, that we thought about paste layer thickness. So idea is that as considering the aggregates that in the mixture proportion, how much thick do we have to coat those aggregates? And of course, as long as we can do it, then we thought that controls the workability. And instead of simply aggregate size distribution, when we thought about aggregate surface area and volume distribution rather than simply size distribution. Then instead of the exposure condition, we thought about lifespan estimated on the basis of damages due to a particular given deterioration conditions. So as long as we have those specific design parameters, and then we will be able to develop the new ECM, particularly for the durable railroad cross ties. And our research team had an options. The first option was we just go with developing the ultra high performance concrete, the so-called the UHPC for railroad cross ties. And the other option is to revise our conventional mixture proportions to make a better and durable railroad cross ties. If you first take a look at the UHPC, actually the definition of the UHPC is ambiguous so far. However, ACI 239 just provides a little bit more specifics about the UHPC. For example, the strength must be greater than or equal to 22,000 psi in SI unit, that is about 150 megapascal. Also, the ACI 239 said the UHPC have no coarse aggregates to enhance homogeneity and introduce fibers for improving ductility and enhancing density by achieving optimum packing density of the matrices. However, the price that you have to pay for using UHPC is $2,500 to $3,000 per cubic yard of the UHPC, as compared to conventional concrete, which is $100 per cubic yard concrete, is quite expensive. Then the question that we had was, can we use UHPC without reinforcements? Because if you can use fibers to the UHPC, then that also provides some of the tensile strength. However, the ACI 239 said that does not mean that you don't need to use the reinforcements. Then the question is how much reinforcement can be reduced by considering the tensile capability of the fibers in UHPC. But I mean, in that sense, quite several researches have been done. However, in specification, no particular design code was provided yet. Therefore, as far as the commercialization of the developing material is one of our research goals, then we wanted to start with revising the concrete rather than starting from the UHPC. So our design criteria is targeting at reducing the reinforcement by 10%. And we expect that can be achieved by introducing fibers. Also, the lower cost is one of our primary goals, and smoothing surface to minimize abrasion damage is one of our important criteria. Also, improving resilience of ECM as regarding the surface state rather than the ultimate state. To achieve those criteria, we thought about maximizing the use of a coarse aggregate to reduce the cost of the concrete and fix the maximum paste volume by 40 to 45% to minimize shrinkage cracks as well as reduce the price point. However, when we consider those maximizing coarse aggregate and fix the paste volume by the 40 to 45%, those two strategies are not really different from the conventional concrete. Therefore, the only factor that we have to carefully consider is how well we design the aggregates. So we thought about we need to consider angularity of the aggregates in addition to the size and surface area. So here is our current achievement. Please note that we are still working on this project for making the better and durable concrete cross ties. But anyways, we use the ternary mixtures for cementitious matrix, which includes the type 1-2 cement, silica fume, and granulated the ground blast furnace slags. Also, we carefully chose coarse aggregates, which is a mixture of granite and basalt types. As a result, we achieved 10,000 psi at 1 day even without steam curing. Also, we got the 12,000 psi after 7 days, and the strength development curve with respect to time is shown on the left panel of the slide. I mean, in addition to selecting carefully all the mixture ingredients, we just try to achieve the optimum size grading curves. Of course, I will briefly explain about how we are going to consider surface area of the aggregates, but at least by using the conventional method, by using the aggregate size distribution, we try to achieve the optimum packing density. So Q value shown on the right panel of the slide indicates distribution parameter. So Q value is going to be the smaller, then you can see that the grading distribution is going to going up and up and up on the right panel. So basically, we had an individual intact the size distribution of the individual aggregates, and by mixing those all different types of aggregates, we just try to achieve a specific the distribution by controlling distribution parameters. So if you see over here, the Q value between the 0.45 to the 0.5, as long as we achieve those lines and mixing those aggregates with that distribution with the cementitious material, we just achieved the 10,000 at the 1 day and the 12,000 after 7 days of the strength, and which is the current status. Of course, we still have a room to improve higher strength rather than what we are showing over here. Another thing that we would like to highlight here is that our mixture proportion that used for this particular concrete is not really different from the conventional concrete. What we did was we carefully selected coarse aggregates, which is a mixture of the granite and basalt. and we carefully chose the size distribution of a mixture of fine and coarse aggregates according to the designated size distributions. One of the differences is that we use 40% of the paste content, which is slightly larger than the conventional concrete. However, as long as we will get more information about aggregates, for example, the surface area distribution, then we'll be able to get the better the control for paste layer thickness that will give us a room to reduce the paste content according to the designated purposes. When we have been interested in the surface area of aggregates, we realized that the surface area is significantly influenced by angularity of the particles. Please take a look at the particle A as compared to particle D. They have the same volume of 0.53 cubic centimeters. However, their surface areas are significantly different from each other because of the shapes. As a result, the ratio between surface area and volumes are significantly different from each other. If you translate it to the mixture design, then you will need more paste content when you use angular aggregates. Then you will have less paste layer thickness if you use angular aggregates to achieve the same workability. For durability performance of developing ECM, we found out that the charge, which is integration of current measurement, is a pretty good indicator for tracing the degree of corrosion. If you see the bottom photos, there are three different states. Number one, there is no visible crack. However, we found out the corroded products were leaked from the top, and then at stage 2, you can see that the slight visual cracks on the surface of the specimen. However, in this stage, you cannot find the longitudinal crack as shown in the picture 3. So, state number 1, 2, 3 are indicated on the graph by the red circle dot and the magenta square dots and the black triangles over here. So when the current is going to be the minimum, then you can see that the leakage of the corroded products, and then you can see the current jump from one to the other, then that is the point that you can observe the slight hairline cracks on the surface of the concrete. And then if you will observe the splitting crack, longitudinal splitting crack, and then we stopped the experiment. However, the current level is quite higher than initial stage. Accordingly, if you integrate the measured current, then you can just demonstrate the right panel curve like this. For structural performance after getting damages, we focused on bond slip responses. Here you can see that the two different responses, one for the intact specimen and the other is for the fully corroded specimens. Herein, the fully corroded means that we observe the splitting cracks because of the corrosion. So as you can see, the peak load is quite different from each other, and the post-peak behavior are quite different from each other. Although the results are quite qualitative and preliminary so far, we achieved the 5100 millicoulombs for developing ECM, which is quite significant improvement as compared to normal strength concrete, of which corrosion resistance is about 100 millicoulombs by our definition of charge. If you translate those values, it means that it will take 50 times longer to observe the splitting cracks because of the corrosion damage. However, again, further researches are required. So if you see the picture over here, after 48 hours of the accelerated corrosion test, ECM looks almost intact as compared to that. Normal strength concrete after 48 hours of the accelerated corrosion, reinforcement is almost significantly corroded and they were broken. In summary, we will keep working on developing a better ECM of the concrete cross ties. Particularly, we will work on constructing database of morphology distributions of available aggregates in Massachusetts. Also, we will investigate the influence of the fibers in terms of the structural and durability performances. Also, we will keep working on calibrating the corrosion damaging models for multiple deteriorating conditions. Finally, I'd like to acknowledge our great supporters. First of all, I'd like to thank to the Lehigh Cement Company for providing all cementitious materials, and I'd like to thank to the Dr. Muchal's team for great collaboration, and I also appreciate to the Dr. Kenneth Hover at Cornell University for his great advices. Most of all, I'd like to thank to our great undergrad researchers, Nick, Cam, Andy, Jacob, Danielle, Pierre, Archer, and Adam. Thanks for your attention. Any questions?